Hi, we're Group 15 in Section C of Intro to Feedback Control, and we are modeling the Tesla SP100D with Cruise Control PID controller. Merging onto highways can be a very dangerous part of driving. In 1999, 19,000 car accidents happened while merging onto high-speed roadways. Control systems can be applied to eliminate instability and grant the user a degree of control. By regulating a system through a feedback loop, control is gained and distractions and stress are eliminated. The control system will ensure the vehicle achieves the desired speed during high-speed merging. Our team decided on 3 goals for this control system. First, the car must reach a terminal velocity of 70 miles per hour, the speed limit on most highways. Second, the car must do so in about 4 seconds to ensure the car isn't merging too slowly. And lastly, the system must limit the overshoot to 10%, so that the max velocity of the car is kept to 77 miles per hour to avoid being ticketed. To model the car, we found that the Tesla SP100D had a mass of about 2,240 kilograms. We also found that it had a 0 to 60 miles per hour pickup of about 2.28 seconds. This corresponded to about 27 meters per second. We were then able to determine the acceleration that this vehicle would require to have this kind of pickup using the equation v1 minus v0 over t. This gave us about 11.65 meters per second squared when you factor in the conversion from miles per hour to meters per second. We were then able to determine the force the motor would have to output on this car to get this acceleration, and we found that to be about 26,000 newtons. The Tesla can be modeled with a mass, a damper, and a force. The mass and force found in the previous calculations are used in this model. B was determined by plotting velocity and adjusting B until the terminal velocity settled at 155 miles per hour. This is the max speed of the Tesla. The drag that achieved this was 370. We can then represent this system as a current source and 2 resistors that can be used to determine the transfer function.
With the model for the system considered, we built the transfer function at that point of the position considering force. And with this in mind, we were then able to take it and derive it, giving us a Vs over Fs. This system then allows us to find velocity from force transfer function. And considering the original parameter of the 26,000 newtons that we need, considering force equals mass times acceleration, we're able to take the system and run a reverse Laplace transform and develop the position, the velocity with time function plotted on the right there. With this in mind, however, we can then go and look at the step function plotted in MATLAB, and this gives us a system that flattens out very nicely, but we have not yet considered all of the parameters. If you look very, very closely, this order ever so slightly. It has no overshoot, but this takes into account dampening at this point. We want the car to be able to get up to a max speed of 155. That is where it tops out, considering this model of Tesla. And 155 miles per hour translate on this plot on slide 8 to 70 meters per second. That's about the equivalency of it. That's with no overshoot. And then looking at the Bodie plot of what we're doing, this works out actually quite nicely as the system is stable. As you can see on slide 9, at this point, Bodie plot is flat up on the left for its magnitude, which means it does not go to New Jersey. It is stable, and that's exactly what we want to see from this system. However, we still need to work on creating a system that we have actual parameters we can meet for the system as a whole. With that in mind, on slide 10, we took this system and constructed a root locus in MATLAB with adjustable parameters, and we had to make sure we could get everything into the white. We were able to do that, and this point, we had to consider the different PID control systems. We decided that it was appropriate that the system have a 10% overshoot with a natural frequency of about 0.55 seconds. This is translated to 4 seconds of rise time to get to our target speed on the highway. Again, drag the squares into the white space, and you create a stable system for the root locus. At that point, we're then able to model out a couple of different PIDs that we like and see which one worked out best. Slide 11 exhibits that we looked at PID for a PID. We also did a PID, and we did on the side look at a PI system, but as the case is with PI systems, it reduces error, but we have parameters to meet. So PD was nice for getting parameters to be met, but considering that we needed an integrating factor, for instance, back on slide 9, without an integrating factor, we wouldn't be able to level out. We would indeed go to New Jersey, and it would not be a stable system. So we ended up considering a PID because it matches both keeping the system stable while matching our parameters that we need for this model for the car. On slide 12, we then show the parameters that looked like they matched up nicely inside of MATLAB's CISO tool. Again, this matches the 10% overshoot that we were looking for, and we wanted to see a rise time of 4 seconds. Got very close to those, very close enough that we were able to do rounding, and it rounded out to a very nice transfer function. This transfer function will then, in the following slides, show the new response, the new Bode plot, and the new nature of the system for.
The block diagram for the PID controlled system can be rearranged so that the force the motor must output can be determined as shown. This block diagram can be further simplified into an inner and outer feedback loop that MATLAB can easily calculate and plot.
The Kp, Ki, and Kd values from the previous slide give us a peak force of about 800, which, when multiplied by our desired speed of 32 meters per second, give a motor force of 25,000 newtons. This value is less than the force the car uses to reach its 0 to 60 mile per hour speed, so it is reasonable. Lastly, we checked that the system was stable and reached a constant speed. Because the slope of the magnitude plot goes to 0 as the frequency goes to 0, the steady state arrow will be close or equal to 0, and the system reaches a terminal velocity. Furthermore, the crossover frequency is around 0.55 radians per second, which indicates a rise time of 4 seconds, which is close to our initial guess. In order to further analyze the stability of our transfer function after the Kp, Kd, and Ki values were all added, we used a Routh-Horowitz table for the closed-loop transfer function. It is clear that the first column of numbers are all positive, indicating that the system is very stable. Finally, we graphed the step response of our final closed-loop control system with a step input of 32. You can clearly see that the system accelerates from 0 to a terminal velocity of 32 meters per second. There is some overshoot, and it is around 10%, as 10% of 32 is 3, and the graph goes to 35.
Lastly, we can see that the rise time is right around 4 seconds, which is one of our goals. This concludes the presentation with the references following.